Today, for my project, I'm going to discuss the science of heat. And I guess I need a pen to do that. The science of heat. This is an important concept because really, when this was coming about, anywhere from 1733 to 1900, we only had as absolutes a gravitational force thanks to Newton, and electromagnetism was not entirely understood or even completely theorized yet. So most of our understanding of the universe and phenomena around us relied on this gravitational idea. In fact, early on, the whole idea of temperature came from the idea that you had some piece of matter with some kind of atmosphere around it, and that atmosphere was called the caloric fluid. And that caloric fluid had its own kind of repulsion to other caloric fluids. So if I had another piece of matter over here, they would push each other away, and the caloric fluid itself would push against gravity, keeping the thickness of this atmosphere based on how much, I'll call it energy or mechanical energy, this fluid around the matter had. So the more fluid, or excuse me, more heat that was in this fluid, the bigger this atmosphere became, which seemed to be a great idea because that meant that as matter heated, it expanded. And this gave you that idea, and then it also repulsed each other, so that increased the mechanical energy of a system. So this was the general accepted process. In fact, some famous scientists like Marquis de Laplace derived a lot of the gas laws from this basis. Now, early on, we in the 19th century, or the scientific community had some idea of the gas laws. In fact, Boyle and we have Boyle's law, Charles' law, and the Gay-Lussac law. But these were all found via, I'll call them phenomenological. They came from industry, coal mining, steam engines, and all of the thermodynamic applications at the time led to these macroscopic relationships. Now, that's really all there was to it. We didn't understand the why whatsoever. It was just the relationships, such as, pressure in one container goes as times the volume goes as the pressure times the volume in a second container, things like that. They all came from industry and application, but there was no fundamental understanding of why they existed. Oddly enough, I use 1733 up here because a gentleman named Daniel Bernoulli, excuse me, I got a bit of a cold, more famous for his, I think he called it hydromatics, but in his treatise on hydromatics, he discussed the idea, and this billiard ball had the idea that there was a conservation of mechanical energy when you had a lot of molecules, and using Newton's laws of mechanics, he could derive this Boyle's law up here, and he put it in his treatise, and he showed that importantly, that temperature goes as some velocity squared, um, as it deals with pressure. So Bernoulli really is kind of the father of this idea of treating thermodynamics as a statistical phenomenon. Molecules, individual molecules. Now, what's important is we don't know about the atom at this point. Not the true atom. Niels Bohr and Einstein and all that will be 100 years after Bernoulli came up with this. Like I said, this is 1733, and really, we're talking about early 1900s, 1910 or so, before this. The funny part, or not so funny, is that this gets lost for about 100 years. No one talks about it or reads it, and we get stuck with our caloric interpretation of heat. And this caloric interpretation has one or a couple major downfalls, one being that it requires matter. So if it requires matter, the question becomes what happens in space. How does heat transfer when there is no matter? But the community was pretty committed to it, because even though you couldn't answer that one fundamental issue, there was a lot going for it, especially in terms of the thermodynamics from a macroscopic standpoint. Now I'm going to fast forward basically 100 years. Gibbs, who is an American physicist, and I don't remember the years he lived, but Gibbs, besides being American, also, forgive my spelling, coined the term statistical mechanics. So that's kind of nice for score one for the team. And then really our friend Planck, who is the first person to come up with the Boltzmann constant. Boltzmann himself never used the Boltzmann constant. This is something that Planck found and then named after Boltzmann, which I find outstanding because I believe the same thing happened with Planck's constant. Somebody else it's not my idea of how I want to approach the kinetic theory of gas, and the more modern interpretation of heat. Because in the end, heat was, and still is actually a little tricky, because heat itself is not energy. We can only talk about transition of heat. And the biggest name really in this field is Ludwig, you have to forgive me if I'm saying it wrong, could be Ludwig Boltzmann, who's an interesting fellow. 1844 to 1906. And the reason he dies in 1906 is because he commits suicide. His greatest achievement was deducing the macroscopic properties of thermodynamics from statistical behavior and random motion, which is quite literally what we call statistical mechanics today. So that's a pretty major give to the community. Just to cover how that works real quick, I think we all know this, but I might as well just quickly review the idea. And I'm going to just do it in kind of one dimension to start with. If we have a box with a particle inside, and it's moving along what I'll call the x-axis, call that X, and we'll make this box L long. This particle will have a collision with this wall, and since its velocity is entirely in the X direction, it will bounce back in that direction. If we make the assumption that it has perfectly elastic collisions with this wall, then we can write a momentum, actually a change in momentum of m velocity in the X direction minus, and then velocity be going in the opposite direction after the collision, so minus, and then the same magnitude. So we can call momentum 2 mass times velocity in the X direction. That was momentum. Yeah, I'm a little worried about notation here. Maybe I'll use different. So I'm going to be talking about momentum and pressure. Maybe I'll put one of these under pressure. And I'm also going to be talking about velocity and volume. Maybe I'll put that on volume so that we know which one we're talking about. I don't want to get confused, so we'll call this velocity and this volume, this pressure and, momentum, and this pressure, and I'll try and keep that throughout. So anyhow, we have a idea of momentum. Now, if we look at Newton's laws, and this is based on one particle bouncing in a 2D frame, we know that force equals mass times acceleration, or we can look at it as the time derivative of momentum. I have an expression for momentum up here, but what's the change in time? So we can look at if a particle, we can really look at time as a frequency. So if a particle, how many collisions does a particle have per time? So the particle starts here and goes all the way over here. It's traveled some distance L, and it traveled that distance over that speed. But that's only one collision, so how long does it take before it has another collision? Well, it should be the exact same amount of time if that started at 0. So now we can say we had 2 collisions in this amount of time, so that's 2L over Vx, and that would be just from a not units but dimensional standpoint, length would be measured in some kind of distance, whereas velocities in some kind of distance per time. So this would cross out and we'd get a time component out of this. So 2L Vx. So now we have a change in time. So going back up here, we could say 2m velocity, that's a sub Vx, over 2L over Vx, which is going to give us, these 2's will cancel, and then we're going to, this V will come up top, so this will give us m Vx squared over L. From here, we can think about pressure because we have a force. So if I come down here and I say pressure equals some kind of force per area, and this is where we may have to start thinking about 3D here in a second, because this is really a wall of types, and that force is being exerted at the wall, so that'd be force per area. But I don't want to get there too fast. I just want to lead out where we're going. Then this would be m, that velocity in x squared over L, which is the length times area, and this you can convert straightforward this part to volume. Area times the length is volume. So mvx squared over volume. And now we have all of a sudden a pressure, which I forgot to put my thing underneath, a volume, and mass and velocity. Starting to look like a gas equation. So just to wrap this part up, I can use kinetic energy here, which equals 1/2 mv squared. Move this into 3 dimensions, and this velocity would become something I can solve for. Really, the mass velocity, something I can solve for. And I would get that as, the main thing is the 3 dimensions means it's going to need to hit all 3 walls. So you divide by 3 because it happens a third as often because it's hitting every wall. So I can write pressure equals what was that? mvx squared on volume. And with my kinetic energy, this was where I wanted to, like I said before, you have the average Vx squared plus the average Vy squared plus the average Vz squared. This is going to give you an average velocity in 3 dimensions squared. And because the time between collisions is a third as often, there's going to be a 3 involved in this, as mv squared on 3 volume. Okay, kinetic energy equals 1/2 mv squared. So I can solve for this mv squared. That's kind of where I'm going. So mv squared equals 2e. And again, we're going to be in 3D, so that's, I'm going to put another 3 here. I don't want to get too far into why that exists. So I can substitute this mv squared up to here, and I get an equation for pressure that looks something like energy K on what was it? So mv squared. So energy K. I don't want to screw this up. EK2. So 2EK. 2EK on volume. How do I say this? If you think about mechanical energy as the average temperature of the system, so we get some kind of 2EK on 3 goes as temperature. I'll do that. It goes as temperature. We can throw a proportionality constant in there and call that T. So now I can substitute let me see, EK equals 3KT. Yeah, I think I messed up a constant here somewhere. Anyhow, the idea is that energy and temperature go as each other. So down here I can get rid of this and put temperature in, and I get it with my proportionality constant. So I get KT on. This is the pressure of one particle or molecule. If we want to sum over states, or really over all the molecules in the system, we can write this, and I'm going to skip a couple steps here. We can write this as N on V, or really just multiply the whole thing times the number of molecules. So we get that, and as you know, that is the ideal gas law. PV equals NKT. It was a little choppy there, but all I really wanted to show was this idea of statistical mechanics dumping the ideal gas law right out. And with the ideal gas law, you obviously, with some assumptions, get your um, Boyle's law, Charles' law, and Gay-Lussac law directly from the ideal gas law. So this shows that statistical mechanics gives us all these phenomenological relationships we already knew about from macroscopic 4. In fact, why that's so important is because he was really advocating for an atom or some kind of atomic material instead of this caloric thing where you had some kind of matter with an atmosphere. He was really specifically talking about some kind of end particles. And if we call these gas particles or atoms, what are these particles? They're atoms. If we think about O2 being oxygen or nitrogen is N2, he's talking about individual types of atoms. And the community did not accept this, and we certainly did not have, like I said, Einstein and Bohr and all their work going on yet. And when he committed suicide in 1906, it was really starting to come about. And that's unfortunate because he kind of gave up right at the time people were realizing that his ideas were and that's him there. Ludwig Boltzmann, chief advocate of the atomic idea. Like I was trying to explain, that was before anybody had an idea, before Niels Bohr had any idea what the atom was. He's the main builder of statistical mechanics, and during his time, he felt along those lines, but he ended up in a lot of bitter debates. He wouldn't leave good enough alone. He wasn't a victim. He would certainly bring those arguments on, but he fought them pretty hard, and never really gave in. He did well, but he didn't make. I guess what I'm saying is he didn't take the path of where I was going with that is that the other big thing he did was his distribution, his probability distribution, which reflected the degrees of freedom of any system. So he generalized this whole idea of statistical mechanics to a general application. The word in some circles is that he may have been bipolar, because he had huge ups and huge downs, great victories and massive defeats, at least in his own mind. And though he may have committed suicide, it may not have been for his science. It might have been he committed suicide, but it might have been for personal reasons. But he certainly, it's a bit of a tragedy because he supported the whole atomic idea before it was popular, and most people didn't give him that credit. It was really Planck who in the end gave him that constant, and then Einstein and Niels Bohr did all their work and really justified him. So that's pretty much it. I just wanted to touch on the science of heat, where we got it right, where we got it wrong, and there were many other ideas besides what we just talked about, but I don't have all the time in the world, so hopefully that gave a little meaning. I appreciate you listening, and have a great day.